My name is Isaac Montoya, and I'm the Marketing Coordinator here at Upsite Technologies. I would like to thank you all for attending our webinar today on the myths of data center containment, what's true and what's not. This is our second webinar of our Airflow Management Awareness Month series. This webinar will be presented by Lars Strong. He is our Senior Engineer and Company Science Officer, as well as an HVAC Specialist and expert in airflow management. He has presented at many industry events and trade shows around the world, as well as participated in many online publications in the industry. Just to give you a brief overview of the company, we were founded in 2001 by Ken Brill and are known as the pioneering company in airflow management solutions. Just in case you don't know about Ken Brill, he also established the Uptime Institute in 1993. Here at Upsite, we are known for our cold lock line of raised floor brush grommets to fill various sizes of openings in the raised floor. This includes the original raised floor grommet, the integral. We are also known for our hot lock line of rack airflow management products to control intake airflow in server racks, and are most well known for our blanking panels. A couple years ago, we also launched our line of aisle lock modular containment to fill the aisle and ensure hot and cold aisle separation. And most recently, we launched our Energy Lock line of environmental monitoring systems, which features both wired and wireless options for monitoring and optimizing the data center environment. And without further ado, I will pass it on to Lars to start the presentation. Take it away, Lars.
Thank you very much, Isaac. Well, welcome everyone. I'm really happy to be here and excited to share this information with you in this way. It's a really nice way to be able to share my experience and share the learnings that we've accumulated over the years and answer any questions you have. There's an opportunity at the end for question and answers, and from the previous webinar that went really well. We had quite a lengthy dialogue about the presentation, so I encourage you as we're going through to jot down questions you have about anything, and then in the lower right hand corner of your screen, you should be able to type in questions, and we'll be able to read those at the end of the presentation. So let's get started. It's a lot of material to cover in a relatively short time. We want to respect your time. We know everyone's busy, so we're going to keep this pretty sweet, but sweet and short. And if anybody would really like to continue the conversation, welcome doing that after the call. So why airflow management? Well, PUE, nobody knew about it, or very few people knew about it about 6 or 8 years ago, but recently just about everybody's talking about it. And when you look at the components of PUE, it's really important to notice that while improving the efficiency of electrical equipment might have a very good ROI and a very reasonable thing to do, you see that it's usually only around 10% of the total consumption of the data center. You know, that percentage is going to vary, of course, greatly depending on what the PUE is of the site. This chart represents a PUE of about 2. And we see here that the mechanical plant and the cooling fans represent 35% of the total data center load. And if you just look at the non-IT, that's 73%. So what does that mean? It means that improving airflow management and the cooling efficiency has tremendous leverage on lowering PUE, lowering operating costs, and recovering stranded capacity. So that's why we want to focus on that. I began my career quite a while ago and did some research with the Uptime Institute, and we looked at a number of different metrics in the industry. We were the first ones to really quantify how well airflow was being managed in the data center. And we found that 60% of the openings in a raised floor were in unmanaged locations, meaning they released bypass airflow. That's a cable opening behind a cabinet or a misplaced perforated tile. And then hotspots, 10% of the cabinets had hotspots, and there was 2.5 times more cooling capacity than IT load. Over the last few years, I've looked at a number of sites. This data on the right is from 45 sites I've looked at around the world, and I found that the bypass open area was 48%, so not much better. surprising that it's still that bad with the amount of awareness in the industry. Hotspots, 20% of the cabinets contained an intake temperature to IT equipment that was higher than the desired maximum. So significantly problems, not getting the job done. That is why a data center is there. That's what cooling is there for, is to provide the optimum intake temperatures for IT equipment. And they weren't getting the job done despite having nearly 4 times more cooling capacity than IT load. Here's a little more detailed data about those sites. You can see the range of area, the smallest one being 720 square feet up to almost 40,000 square feet. Number of cooling units, just 2 to 40, so an average of 8 cooling units in the room. There's that 48% bypass open area. Hotspots on average were 20%. I started looking at cold spots and some of the later sites that I looked at, and found that 35% of the cabinets contained an intake temperature lower than ASHRAE's minimum recommended intake temperature. So as many of you are probably well aware, ASHRAE recommends intake temperatures, worked with computer manufacturers, hardware providers to define what is the intake temperature that will produce the maximum reliability. And they defined that as 64 to 80.6. And so I found a number of intake temperatures lower than 64 degrees. And when there's intake temperatures lower than the minimum, that's a very good indication that a lot of cooling capacity is being used and cooling supply temperatures are lower than they ought to be if airflow management were improved. Perforated tile placement was on average 77%. So what that means is that I looked at every perforated tile and found that 77% were in front of IT equipment, where they ought to be, where the air coming out supplied the cooling needs of some IT equipment. But 23% were out in open areas or out in hot aisles and just contributing to inefficiency. So that's one of the simplest ways to improve airflow management. I'll talk about that more later. The cooling capacity factor is a simple metric that we developed that really very quickly identifies what's the opportunity for improving the airflow management in the computer room. It's simply a ratio of the installed cooling capacity to the estimated heat load. And I'll show you later in the presentation how to calculate that. But that's that number 3.9 times more cooling capacity running than there was IT load. All right, so let's talk about a number of different areas in the computer room. And the first one is the raised floor. It's really important to seal the openings in the raised floor. Here's a picture of a large cable cutout, and it's quite possible for an opening this size to waste an entire quarter of a cooling unit. 4 of these openings, and all the air from one cooling unit is lost out of such openings. So the first place to focus on is the raised floor. Here's an example of how these raised floor openings ought to be treated. Of course, sealed. Here's with brush grommets. And whether it's our product or somebody else's product, these openings need to be sealed. That's the first step in getting the air where you need to get it. All right, for those of you well aware of a lot of this science, I'm getting to the point, I'm getting to the good stuff, but wanted to lay the groundwork. Here's one more slide talking about that, which is that IT intake temperatures are the most important thing in the room. I'm very often asked, what's the right set point for my cooling units? Or how many perforated tiles should I have? Or on and on and on, many different questions. And the answer is usually something around, well, it depends on the IT intake temperatures. You want to have your supply temperatures as high as possible without causing intake temperature problems to the IT equipment. In this picture, it's an extreme example of a site I found where most of the equipment in the cabinets was too cold. That's everything blue and purple at the bottom. And in the top, everything orange and red is overheating. The only IT equipment receiving the proper intake temperature is that blue and green, about 3 or 4 U band right through the middle. Everything else is too hot or too cold. And this wasn't due to a lack of cooling capacity. It was due to a lack of airflow management and trying to supply cold air to deal with the hot spots. A very inefficient way to get at the problem. All right, so why are there so many problems? Well, there's a lot of awareness, but the implementation is pretty poor. Airflow management, air movement is invisible to most people. We rarely get to see it. We sometimes see leaves blowing around or dust blowing around in the wind, but we rarely get to see how air moves around in a computer room. So one thing that might be helpful is to consider water. And what would water do if it were moving around? Water is a fluid, just like air, and the same equations apply, just different densities. So when you're wondering, what's the air doing in this room, you might find it helpful to consider what would water do if it were coming out of this tile and flowing around this cabinet or over the top of the cabinet or trying to flow back to the cooling units. That might be helpful. Another problem is that in the US, we refer to cooling capacity in terms of tons, and very few people can define a ton, but they all know how many tons of cooling they have in the room, but it's a unit that nobody can compare directly to the most prevalent and most important unit, which is kilowatts. So it's really easy to convert tons to kilowatts simply by multiplying by 3.52, and then you can compare apples to apples and have clear understanding of capacity versus load. Another problem is vendor influence. A lot of people are touting the silver bullets and that their solution will answer and solve all your problems. When data center managers are having a hard time, they often go to cooling unit manufacturers, and this was much more prevalent in the past. It's getting a lot better. But they'd ask, a cooling unit manufacturer for advice. What do I do to get rid of this hot spot? And they'd scratch their head for a microsecond and say, well, it looks like you need to buy another cooling unit. So many more cooling units got installed in rooms than were necessary. It was a lack of airflow management, not a lack of capacity. The good news is all of these things create opportunity to reduce operating costs, defer capital expenditure, increase the cooling capacity of the room, how much IT equipment can be added. Very important for both enterprise and co-location facilities. Ultimately, IT reliability. And last but not least is green initiatives, and the goal to be a good corporate citizen and reduce our carbon footprint. And just looking at those sites and doing some rough numbers, just by improving airflow management in computer rooms, it's not unrealistic to be able to save significant money, $60,000 annually in operating costs by improving airflow management. Of course, if your site has already done a rigorous process of sealing the raised floor and installing blanking panels, maybe you've installed variable speed drives on your cooling units and you've reduced fan speeds, then that $60,000 you've already been benefiting from some of that and taken advantage of some of that savings. But there's a lot of savings left on the table in most cases. All right, let's get into it. First myth, containment eliminates bypass airflow. Well, the very simple definition of bypass airflow is any conditioned air that comes out of a cooling unit and that does not pass through IT equipment before returning to the cooling unit. So I'll show you a couple of graphics that hopefully will clarify this. In this image and the three following, all of the cooling units in the room are represented by this one cooling unit, and all the IT equipment in the room is represented by these two rows. So we look at all the air moving through all the cooling units, and it's 10 units of air. Doesn't matter if it's liters per second or cubic feet per minute. 10 units of air is moving through all the cooling units, and so if 10 goes under the floor, 10 is going to come out of the floor. And in this case, we have 4 units coming out of supply tiles located in the cold aisle. That's what we want. But we also have 6 units of air coming out of unsealed cable openings behind the IT equipment. The IT equipment is consuming 4 units of air, 2 in each of the rows. So a total of 4 units of air is sucked up by all the IT equipment. Well, we have 4 units delivered to the cold aisle, so the IT equipment might be happy in this case. We've got enough conditioned air supplied to the aisle for what they are sucking up. Everything might be just fine in this room, except we're moving more air through the room than we're moving 10 units when the IT equipment only needs 4. So after sealing those cable openings, which is of course a good idea, we now direct all the conditioned air into the cold aisle. So instead of 4 units of air, we now have 10 units of air coming into the cold aisle, but the IT equipment only needs 4. And so we have 6 units of air leaving the cold aisle as bypass airflow. Now this relates to the myth. A lot of people believe that, well, all I have to do is put full containment, put a cap on top of that, and now I've eliminated bypass airflow. Well, that's not true. It's not true at the room level. It might help at the row level or the rack level, the amount of air, conditioned air bypassing a rack, but it won't help at the room level. You still have 10 units of air moving through the cooling units, 10 is delivered into that cold aisle, and now assuming that the containment is very well done and sealed up completely tight, where does that 10 units of air go? Well, it gets stuffed through the IT equipment. The IT equipment in each row was only needing 2 units of air, but now we're pushing an extra 3 units of air through that IT equipment. It's still another form of bypass airflow. So what does airflow management do? It creates the opportunity to optimize the cooling and to more closely match the amount of air moving through the cooling units with the amount of air required by the IT equipment. So after sealing those cable openings, we had too much air in the cold aisle, and so we could reduce the fan speeds and more closely match that supply to demand. In this picture, we don't have any containment in place. We may need doors, or maybe we need baffles, or maybe we need full containment. That depends on a number of considerations, a number of design issues in the room. The height of the ceiling, obstructions, the layout of the equipment in the room. It depends on how much airflow management is necessary, how much blockage to separate supply and return air to be able to reduce fan speeds. And the more blockage, the more airflow management there is in place, the lower the fan speeds can be, the more closely that supply and demand can be matched. All right? Going to myth number 2, containment improves efficiency, it reduces costs. Well, there's only one caveat to this, which is if airflow management or containment is put in and it reduces the intake temperature of the IT equipment enough that the fan speeds in the IT equipment slow down, then those fans will be using less energy and there will be a reduction in cost, but it's generally very slight. Most computer rooms are not operating with a lot of their IT equipment with intake temperatures in the 80s or the 90s, causing the fans to go very high. So this is usually very low. As I mentioned before, putting in containment creates the opportunity for efficiency and cost reductions. Here's an example of a cooling unit that shows the cooling capacity at various return air conditions, at 2 different conditions. The top line there is 72 degrees and 45% relative humidity. And we see that in that case, there is no latent cooling, and the total capacity is 67 kilowatts, and all of it is sensible capacity. So that's the desired, that's where you want to get to. A lot of rooms, or let's say the room before airflow management, was operating with a return set point on the units of 70 degrees. And at that condition, there was a total, the cooling unit only had the ability to remove 64.5 kilowatts of heat. and 4.8 kilowatts of that capacity was being consumed by heat given off by moisture condensing on the coils. So nature does this interesting thing that when moisture condenses, it gives off heat. And in this case, it was giving off 4.8 kilowatts of heat. That leaves 59.7 kilowatts of cooling capacity to reduce the temperature of the air to take the heat out from the IT equipment. But if you change the set point up to 72 degrees, then all that latent cooling goes away, no more moisture is condensing on the coils, and you get all the sensible capacity out of the cooling unit. So these 2 points were cherry-picked out of all the potential places you could pick the conditions. Obviously, going from 72 to 74 degrees is not going to see an 11% increase in sensible capacity. But there are a lot of data centers that are right at this threshold. They're operating with a little bit of latent cooling. There's some moisture condensing on the coils. And if they're able to raise the set point, either supply or return, then they're able to get rid of that latent cooling penalty. All right. Here's another example, really extreme, 40% increase in sensible capacity, going from a 65-degree return air control to 72 degree. Now, there's not that many sites operating at 65-degree return anymore. We're getting better and better. But just another example of how much capacity can be realized by changing the set point. Get into myth number 3. Perforated tile placement is always important, whether there is containment in place or not. And I've seen a lot of rooms where full containment has been deployed, and they didn't think that perforated tile placement mattered, that they would put 2 full rows of grills or 2 full rows of perforated tiles in the cold aisle, and that wouldn't matter. If they have control of the fan speeds based on static pressure, then perforated tile placement may not be as crucial. But as I showed you in that explaining bypass airflow, if there's too much air supplied into the contained cold aisle, then that air is going to be stuffed through the IT equipment, and it's going to be lost as well. It's another form of inefficiency. So making sure that the static pressure in the cold aisle compared to outside the cold aisle is just very slightly positive is very important for making sure you're optimizing the cooling in the room. And that can be done either with controls or simply by measuring it. If you open the doors to your containment and a lot of air rushes out, then too much air is being supplied. The IT equipment is not needing that much air. I was in one site, and they had previously put in meat locker curtains, and they said those didn't work because they blew out sideways like a skirt, standing over a fan. And they pulled those out, and they put in hard containment and thought that solved all their problems. But all they had done was mask the problem. In reality, what they could have done is just reduced fan speeds or turned off cooling units until those curtains hung vertically and stopped blowing out sideways. And then they would have known that the amount of air delivered to the cold aisle was balanced with the amount of air the IT equipment in that cold aisle was demanding. So here's just a plan view showing perforated tile placement. Every perforated tile should be intentional, every single one. Quite often I find perforated tiles out in open spaces, lower right-hand corner, that are near the door, and I ask why, and people say, oh, that's so that when my boss comes to poke his head in the room, it feels cool. Well, that is not a justified reason for having perforated tiles in open areas. And I often find perforated tiles in hot aisles. Now, it may or may not be a bad thing to have one there. The only reason for a perforated tile, supply tile in a hot aisle, is if equipment has been installed backwards and there is an intake in that hot aisle. well, that's fixing it, that's treating the symptom and not the cause. What needs to actually happen is that equipment needs to be turned around so that the intake is on the cold aisle ultimately. Okay. Myth number 4, we're getting through them. Just a couple more to go, and then we'll share a few more concepts with you. So please, a reminder, if you have any questions, particularly if you disagree with anything I say, appreciate you bringing that up. We can all learn from those moments a lot more than just agreeing with each other. So this one's a little more controversial. Containment increases the return air temperature to cooling units. This myth is not true for a couple of reasons. One is that assuming we have return air control, or even if we have supply, that's a thermostat, and that cooling unit is going to work to maintain that same return condition. So if the air temperature, if the amount of load in the room is not changed, or if the amount of air moving through the room is not changed, then that thermostat is going to work to maintain the same temperature. So it's not going to change unless you change the thermostat. Another way to look at this is that if you have the same amount of flow, the same amount of flow rate of air moving through the room, and you're adding the same amount of heat to that air, regardless of whether there's containment or no containment, then the increase in temperature is going to be the same. So just putting containment in alone will not change the return air temperature. It only separates, to some degree, the supply and the return air. But ultimately, those are all going to mix. They're going to all come back together and mix by the time they get back to the cooling unit. Here's an infrared image that shows this real clearly. So we're looking down on the top of a cooling unit, looking down on the return. These are the filters across the top of a cooling unit. And we see a couple of rows of equipment over there to the left. And there's this really nice warm air pocket in the middle of 85-degree air is coming into the middle of the cooling unit. And it's surrounded by air returning that's 10 degrees cooler, 11 degrees cooler. And what this very clearly shows is that there's some of the air that came out of this cooling unit, passed through IT equipment, it got warmed up, and is returning to the cooling unit at 85 degrees. But a significant amount of the air didn't pass through IT equipment, and it's returning to the cooling unit at 74 degrees. It probably came out of the cooling unit a little bit cooler, and it's mixed a little bit and warmed up a little bit, but a very clear distinction between the air coming out of the hot aisle and the air that bypassed the IT equipment. Now, you might say, well, what if you just extended these cooling units up to the ceiling and you went with hot aisle containment and ceiling plenum return? Wouldn't that make all the air warmer? It would even out all the air because there would be a longer path and there'd be more disruption and more mixing. And what we would see is if you put in hot aisle containment, fully contained it, and put it up to the ceiling, ducted this cooling unit up to the ceiling, then all the air returning to this cooling unit would be an even temperature, and it would be somewhere around 80 degrees, assuming that the flow rate of the 85-degree air and the flow rate of the 74 is 50-50. It would be blended, and it would be mixed up and all be 80 degrees. And we wouldn't see this separation, but it wouldn't change the efficiency of the system. There would still be a portion of the air that was bypassed, and there would still be a portion going through the IT equipment. All right, the last myth. Full containment is essential. Partial containment doesn't work. This is not true because, as I explained earlier on, when you put in full containment, it doesn't change the amount of bypass airflow. The goal in any airflow management improvement, whether it's raised floor grommets or blanking panels in the cabinets or containment, is to create enough separation between the hot exhaust air and the cold supply air so that the flow rate can be reduced of the conditioned air flow rate can be reduced, and the temperature of that supply air can be increased as much as possible without causing intake temperature problems. And in many cases, just doors alone can create significant benefits. A lot of airflow management problems result from air wrapping around the ends of rows. And just by putting on doors at the ends of the rows, that may be enough to significantly reduce fan speeds and raise temperatures. Also, sealing the racks very tightly is one of the most important things to do. Got a couple of images to show you following this that explain that. And then air can be wrapping over the top of the cabinets and coming into the cold aisle. And even just placing baffles, blockages on tops of 1 or 2 or 3 racks can significantly affect hot spots and improve conditions in the room. So let me show you a couple of specifics here. Here's a fully contained cold aisle. You can see in the lower right hand that green handle, and the door was just opened so that we could see in with the infrared and see the intake temperatures to the IT equipment. Here's a case where full containment really did not help at all. We have a bunch of equipment that's too cold at the bottom, and we got some intake temperatures at the top that are pushing the ASHRAE recommended maximum. And the problem here is that there were missing blanking panels in the cabinets, and there wasn't sufficient static pressure in the raised floor. There wasn't enough cold air coming out of the supply tiles in this aisle to satisfy the demands of all the IT equipment. So containment didn't solve the problems. Basic airflow management prerequisites were necessary. And had those been implemented, had all the cable openings been sealed and blanking panels been put in, conditions in the entire room would have improved, and containment wouldn't have been necessary in this aisle. Here's another couple of images. These are CFD images, computational fluid dynamics, or engineering simulation of a room, showing a cold aisle with baffles over the top to prevent any hot air coming over the tops of the cabinets. But each of these rows has a space underneath the cabinet. And what's happening on the left, we can see, is that hot air is flowing underneath the cabinet, coming into the aisle, into the cold aisle, and that prevents the cold air that's there from being able to be pulled in by the IT equipment. So the equipment in the bottoms of the cabinets have significantly higher intake temperatures than just above. And after sealing these openings, that air is blocked, and the cold air that's there is now available to go over to the IT equipment and solve that problem. Okay. Here's another engineering simulation showing 3 cross sections through 3 rows. And we've got a hot aisle and a cold aisle here. And we're going to focus just on the cold aisle over on the right side. And we see that at the cross sections, which are placed just inside the ends of the rows, there's significant areas of hot air. And that's from the air wrapping around the ends of the rows, both at the top and bottom of these rows. Also, we see that in the middle cross section, there's warm air right near the tops of across the tops of the cabinets, and very close to that front edge of the cabinets. And that can wrap over and cause intake temperature problems, hot spots on the very top 2 or 3U. So then we add baffles across the tops of the cabinets and doors, and these prevent the air wrapping around, and it's enough of a blockage to get rid of all of the hot spots and contain that cold air enough that now we see no hot air wrapping around the ends of the rows, and across the top, that space between the baffles. And I'll show you what we're talking about by baffles on the next slide. That space allows the cold air to exit, and obviously if cold air is flowing out of that opening, then no hot air can flow in. And so these are the products that we've developed for containing aisles. They attach magnetically, and they're modular, so 1 piece per cabinet. And these can create enough of a blockage to be able to balance that airflow. Okay. There's another one, the rack gap panel for sealing spaces between cabinets, a really important thing to do. And then angled baffles for cold aisles and vertical baffles for hot aisles. It's important not to restrict the air flowing out of the hot aisle because that will increase the likelihood that hot air will flow through the cabinet. You want to just direct the hot air out of the hot aisle and get it moving on its way back to the cooling units. Okay. So in optimizing a room, there's an important consideration. Every computer room in the world can be placed in one of two categories. Those with no IT equipment intake temperature problems and those with IT equipment intake problems. So if there are intake temperature problems, then improving airflow will get rid of the hot spots and make it more efficient. But there's a lot of people out there that say, oh, I've got no problem. I've improved airflow. I'm good. And IT equipment is all happy, no hot spots, no cold spots. But the question is, can they be more efficient? And one of the easy ways to look at that is with a metric that we referred to at the beginning, which is the cooling capacity factor. And again, it's simply the ratio of the rated cooling capacity to the estimated heat load. So here's an example of how to calculate that. In this example, we've got 7 30-ton cooling units. That's 210 tons of cooling, and we have a UPS load of 235 kilowatts. So we want to know what's the total rated cooling capacity in kilowatts. So we take the 210 and multiply by 3.52, and we come up with 739 kilowatts of cooling capacity. We take the UPS output load of 235 kilowatts, and we multiply it by 1.1 to add 10% just to estimate the additional heat load in the room. There's a lot of reasons the heat load could be significantly more than 10% on top of the UPS load, or it could be less. But just to get a quick estimate, we add 10% to the UPS output, and we have 259 kilowatts. And then you just divide 739 by 259, and we have a ratio of 2.8. There's 280% more rated running cooling capacity than there is IT load. Of course, the amount of heat being removed from a room is always going to equal the amount of heat being added to the room, or the room would be warming up or cooling down if that was out of balance. But the question is, how much cooling capacity do we need to running to do that job? How well can we utilize, what's the utilization of that capacity to remove heat? And we want this ratio to be as low as possible. Those 45 sites that I looked at, the average was, this ratio was 3.9. And out of those 45 sites, 6 of them had a 1.2. And so what that looks like is if you have a, we'll just use some real simple numbers here. If you have a megawatt of heat load and you have a cooling unit that can remove 100 kilowatts of heat, then you need 10 cooling units to remove a megawatt, and you'd have 2 extra or 2 redundant cooling units. So that would be a 1.2. And just 6 of those sites had a 1.2, so quite possible, but a lot of room for improvement in a lot of sites. And the reason for this, the desire to get the cooling capacity factor as low as possible refers to what I shared earlier about how the cooling capacity of cooling units increases with the return air temperature increasing. And you get more capacity with a higher return air temperature, and you get less capacity with a lower return air temperature. So there are a lot of computer rooms that are running with the return air temperature lower than the rated capacity. most cooling units are rated for around 75 degrees return air temperature. And so if your return air temperature is anything less than 75 degrees, straight out of the gate, you're not able to get the rated capacity. And then the benefits of reducing fan speeds. If you have 80% fan speed, then you'll have 80% airflow volume. So you've reduced the fan speed by 20%, and you've reduced the amount of air you get by 20%, but you reduce the fan energy consumption by 50%. And that's the advantage of variable speed drives. Ultimately, when you really want to get down to this and refine things, you want to calculate how much air is moving through the IT equipment and how much air is moving through the cooling units, and get those two as close as possible. And this comes down to the heat transfer equation. And the general one that applies to everything is there on the top, and the bottom is simplified for the units that we deal with here in North America. It's the constant of 3.16 and delta T in degrees Fahrenheit and flow rate in CFM. So how this plays out is if the delta T through IT equipment is 20 degrees, you know, that middle bullet point there, pizza box servers, one-use servers, lower delta T's, or any IT equipment with a lower delta T. If it's 20 degrees, then that equipment is going to consume 158 CFM to keep 1 kilowatt cool. IT manufacturers are designing equipment to be as efficient as possible. And one of the ways they can do that is to reduce fan speeds and let the delta T go higher. So if the delta T through the IT equipment is 35 degrees, then only 90 CFM is required to keep a kilowatt cool. And this can have a huge effect on the amount of air required in the entire room. So if you take the UPS load and you multiply by the CFM required per kilowatt, you get the total IT CFM. There's a number of tricky points in this calculation. Delta T, of course, of the IT equipment varies by time, and it varies by equipment. So depending on how homogeneous or irregular your equipment is, your equipment mix is in the room, that delta T figure can be easy or hard to calculate. But this is what it comes down to. So here's the key metrics that I suggest everybody calculate. Even though they seem rather remedial in some cases, I really encourage everybody to know them. IT equipment intake air temperature for every piece of IT equipment can easily be done with an infrared thermometer or an infrared camera. Monitoring is an essential aspect of airflow management and computer room operations, but it can't pick up everything. Surveys are also required with these other tools. Calculate the cooling capacity factor to see how much room there is for improvement. Raised floor open area simply requires somebody with a clipboard, a flashlight, tape measure, spending the time necessary to measure every hole in the raised floor and quantify how many square feet of bad open area are there and how many square feet of area in cold aisles are there. What's that ratio of good to bad? Every perforated tile should be in the right location, and as we all know, those tiles tend to move around in rooms sometimes, depending upon how strict the management is in the room. Blanking panel utilization, every single opening in a cabinet should be filled. The only way air should be able to move through IT equipment, move through a cabinet, is through IT equipment. And then ultimately getting bypass airflow as low as possible. So to help you with this process, we've developed this holistic approach. It's called the 4 R's of airflow management. It helps people focus and pay attention to the 3 elements of airflow management, which are rack, row, and raised floor. And that after making improvements to any one of these 3 elements, say installing a bunch of blanking panels in the racks, it's important to check in at the room level and see if fan speeds can be reduced, or supply temperatures can be increased, or chilled water temperatures can be changed to realize those benefits. And then go on and focus on another area of the room. Look at the row and install containment of some form And then once that's installed and balanced out, look at the room level and see what adjustments can be made to realize savings. We've got a link there for a video that we put together on this concept, and imagine you'll find that very helpful. We have 2 more webinars coming up this month. June 15th, we'll talk about how IT decisions impact facilities, and I'll be joined by Ian Seaton to discuss that very important topic. If there aren't management changes and if management isn't behind these changes, it's impossible to really optimize the operation in a computer room. Management structure and management decisions have a significant impact. And then we'll finish up the month with the 4 delta T's of airflow management. And I suspect you'll find this really enlightening to see how there are actually 4 delta T's in a computer room. There should be just 1, but there's often 4. So look forward to sharing those topics with you in the future. Here's my contact information. We're going to start looking for questions and have that conversation. And as I said before, welcome any follow-up conversations. By phone is obviously the best way to discuss these topics. And first question, probably everybody would like to know, or will this presentation be available? And yes, it will be. We'll send out a link to that, a reminder, a follow-up email after this presentation. Another question here, if heated exhaust may be collected and returned to the crack, returned via duct, does it increase system delta and can improve overall system efficiency? So I believe I understand your question, which is yes. The more that the hot air can be contained and returned to the cooling units without mixing, the more efficient the system can be. But remember, if you've got a room that's operating and you install a bunch of ductwork, or say you fully contain a hot aisle and duct it to the ceiling and use the ceiling plenum for the return, and you duct the cooling units up to that ceiling plenum, doing those things will not increase the efficiency of the overall system. You have to make changes after you've done that to realize those benefits. Putting in that ducting, utilizing the ceiling plenum, creates an opportunity to reduce the flow rates and increase the temperature set points. There are some computer rooms with full hot aisle containment that are seeing return air temperatures to their cooling units in the 80s and the 90s, and even the high 90s in some cases. And we'll talk about this a lot more in the 4 delta T's. With so many manufacturers of equipment, IT equipment with different delta T's, what suggestions do you have for calculating the airflow demand of a computer room overall? Good question, Mark. I would look at the different types of equipment I have and see if I could group it together. Measuring the delta T of the IT equipment is not hard to do individually, and so you can check a few different types of equipment and see what the delta T is across the different types, group it into those different categories, and then look at how much load is being consumed by those different types, those different groups of equipment. It's all a matter of, how fine do you want to sharpen the pencil? How close do you want to get? You can do a real gross room level estimate, or you can then go and work down to the row and the cabinet and the IT equipment level. But I would suggest starting with grouping it and saying, I've got about 3 different types of equipment in the room, or 5, whatever the number is, and then go measure at a number of locations what the delta T is of those different types of equipment, and estimate it in that way. And then very quickly you'll start to get an understanding of what's going on in the room, and and where else you need to look to start to refine those numbers. And just getting the process started can be really helpful. Getting people making those measurements and starting those conversations can be a really helpful thing to do. The ton capacity of cooling is the nameplate of the cooling capacity for sensible heat. I mean we have 30 tons, but they specify only 20 tons of sensible heat. Yeah, so every cooling unit has a chart, and I showed you a couple of rows out of those charts. Every cooling unit has available for it, either in the manual or available from the manufacturer, a table listing the different capacities for different return air conditions. So your cooling unit that says 35, but or says 30, but only has 25 tons of sensible, is for a very specific condition. It's possible when you reduce the relative humidity is lower and when the return air temperature is higher, that you can get the full 30 tons of sensible capacity out of that cooling unit. You can even get more. You can get 31, 32 tons of capacity out of a cooling unit if the return air temperature is warm enough. Another question here, can you use kilowatt consumption of IT equipment in a contained aisle to calculate required CFM for the aisle? If so, what is a good baseline CFM value to use for the calculation? Can slide 35 be applied? So yeah, this comes back to you've got to know what the delta T is of that equipment, and then using the kilowatt consumption for that aisle is totally an appropriate way to calculate the CFM. And so slide 35 is the way to look at that. I've got a more detailed table, or you can do the math pretty easily with those equations in the presentation to determine what the CFM rate is for each of the delta T's. But I'd be happy to share that with you if you want to contact me offline. Next question, are you also recommending blanking panels be used in open rack units in the rear of the cabinets as well as the front? Great question, Mike. There's a lot of confusion about this, and definitely not. The only place that blanking panels are needed is at the front of the cabinet. And creating a plane across the intakes of the IT equipment, that the only opening in that plane is through the IT equipment. So I mentioned blanking panels, and they need to be between all open spaces in the rack. But another really important area is the rails to the sides of the cabinets. Quite often this is also open, and that needs to be sealed as well. Another question, what control strategy do you recommend to match cooling airflow and IT load required airflow in a 100% OA data center? I'm not sure what the OA stands for. There are a number of cooling control strategies. A lot of people are managing fan flow rate on raised floor static pressure. And this doesn't really get at what the IT demand is. The only way that static pressure of the raised floor is going to control fan speed is if you take out some solid tiles and install some grates, then the static pressure will drop because the raised floor open area increased. The sensors will calculate that, will notice that, and they'll speed up the fans to pressure to put more air into the floor and get the static pressure back to the same state. So what this guarantees is you have the same amount of air coming out of the floor all the time, but it doesn't pick up the demand of the IT equipment. Another way to do it is to manage fan speeds based on static pressure in a fully contained cold aisle. And that way, when the IT equipment speeds up and it sucks more air out of the cold aisle, the static pressure in the cold aisle will drop, and the controls will increase the fan speeds to supply more air to that fully contained cold aisle. So your question is a really good one, but it's really hard to answer it without a lot more information about what is the configuration of your specific room. Basically, as airflow management increases, then the controls, the appropriate control scheme changes. Another question, when does ducting the crack returns to the ceiling plenum actually help? Well, this relates to the question of what's better, hot aisle containment or cold aisle containment. Hot aisle containment has a number of advantages, but it requires a way to get the hot air back to the cooling units. And so if you have a ceiling plenum, then that can be, that's the way to get the hot air back and do hot aisle containment. And I'd say using the ceiling plenum always helps, because it really significantly reduces the likelihood of hot air mixing into the cold aisle. And so by getting the hot air out of the hot aisle and up into the ceiling, and the only way for that air to get back to the cooling units is because the cooling units are ducted to the ceiling, then that can be a really dramatic improvement in the airflow in the room and enable you to have significant savings, especially if you have variable speed drives on your cooling units. You should be able to significantly reduce the fan speeds and raise the supply temperature. Next comment is not a question, but related to the myth that containment does not increase efficiency and reduce cost. Yeah, I'm not sure. I understand if you want to, Daniel, if you want to say more about that, I'd be happy to comment if you can clarify a little bit more. It happens to the fire system inside. What happens to the fire system inside the containment? Fire suppression is a really significant issue related to containment. A lot of containment solutions used fusible links, and so a fusible link is a link that when it gets hot enough from a fire, then it melts at a low enough temperature and the containment drops on the floor. But that is no longer allowed by the NFPA. And so any containment structure that fully obstructs the fire suppression needs to be tied into the sprinkler system. It needs to be tied into the smoke detection system, that is, so that when there is a smoke sensor activation, then the containment will get out of the way in some way. By some mechanical means, will either drop out of the way or roll up or somehow get out of the way. And so these solutions are effective, but they're also very expensive. Another way to address it is to put the fire suppression inside the contained space. And that means dropping the sprinkler heads down inside the full containment. Again, very costly and expensive. Then there's also the consideration of the gaseous fire suppression. And some studies have shown that gaseous suppression is not hindered by full containment, but some fire marshals, some local authorities are not accepting that and saying that full containment does obstruct gaseous suppression. So ultimately it comes down to having a conversation, getting approval from your local authority having jurisdiction. Another question. We have a hot aisle containment system, and we are controlling the CFM to the IT equipment through the differential pressure across the rack of just 0.02 inches water column. We're still having issues, though. Alan, that sounds like a good approach, but obviously, something's going on, and I don't know what it is. Be happy to discuss that with you. offline because that can get pretty complex, but that's a reasonable approach from what I understand you're doing. When does hot aisle containment make sense instead of cold aisle containment? We'll kind of address this already. Hot aisle containment, in my opinion, is what you want to try and go for, but it requires being able to contain that hot air all the way back to the cooling units. And so hot aisle containment makes sense generally when you have a drop ceiling, when you have a ceiling plenum that you can use to get that hot air back to the cooling units. So lots of questions. Really appreciate everybody's interest in trying to work through them. Is there a recommended underfloor pressure to shoot for when attempting to shut down crack units? This would only be done after addressing the airflow in the room. Great question, Timothy. And the answer is no. There isn't a specific underfloor pressure to shoot for. That comes back to my comment earlier, which is the underfloor static pressure you want to shoot for is as low as possible without causing IT equipment intake temperature problems. So it also relates to what type of supply tile you're using. If you're using grills with large open areas, then they will create much less restriction and not as much pressure as necessary to get the same amount of air out of the floor. So that's really a balancing act and an iterative process, meaning as you improve airflow management, you address it in some area of the room, then you want to reduce fan speeds, shut down as many cracks as you can, kind of until you have IT equipment intake temperature problems, and then turn the cooling unit back on so you don't have any problems. And then after you've done more airflow management, you might be able to turn off another one. So hopefully that's helpful in iterative process. Sure. Oh, OA, outside air. Thank you very much for that clarification, Tim. And so going back up to the beginning of it was, we're just looking for the rest of your question. So the question was, what strategy do you recommend to match cooling airflow and IT load required airflow in 100% outside air data center? So yeah, 100% outside air means that there's no recirculation. All the air that goes into the IT equipment is coming from outside, and all of that air gets exhausted to the outside. So by design, they should match. There's various ways to do this. Talking to a few people in the industry, there are some that are experimenting with extreme ends of the spectrum, and they're using no fans other than the IT equipment fans to move that outside air through the room. So they have huge banks of filters with very low resistance, very low pressure drop across the filters, and they have perfect separation from the cold aisle side to the hot aisle side, so that the server fans and the small static pressure that they can generate is enough to pull outside air into the room through the IT equipment and out the room. So that's one extreme case. If you're using fans to pull the air from outside and blow it into the room, then having too much air blown into the room, some of it blowing over the cabinets or around the cabinets or through the cabinets, mixing with the hot air before it goes outside, doesn't cause any problems, but it does mean you're using more fan energy than necessary. So it's kind of the same strategy. Reduce the amount of air being pulled in from outside until you start to have problems, until there's a number of ways to measure it is intake temperature to the IT equipment, or static pressure differences between the cold side and the hot side of the equipment. So kind of a complex question to try and answer here, but hopefully that's helpful. And again, happy to discuss it more with you in detail. We've got just a few more. Really appreciate everybody hanging on and discussing this with us. If well-contained and well-flow balanced, how close should the coil delta T be to the IT delta T? Great question, Mark. Ideally, they will be the same. And the challenge there is having homogeneous IT equipment, homogeneous IT delta T, and also having cooling units designed for that delta T. So IT equipment is being designed with generally much higher delta T's than the cooling units were designed for. But I know of data centers that are working with the cooling unit manufacturers to have custom-built cooling units designed for, say, a 40-degree delta T. And therefore, you can have the flow rate of the cooling units perfectly match the flow rate of the IT equipment. And I appreciate your question because it does add some clarification. I've mentioned, in general, that the goal is to always reduce the flow rate of the cooling as close as possible to the IT equipment. But when the delta T's are significantly different, that can be impossible to do. For example, and I'll try to explain this over the phone now, is that if the IT equipment has a delta T of 40 degrees and the cooling units can only deliver a delta T of 20 degrees, then there has to be twice as much air moving through the cooling units as moving through the IT equipment. So in that case, there has to be 50% bypass airflow. So there's 20-degree delta T across the cooling units. Half of that air gets warmed up 40 degrees, and half of the air coming out of the cooling units doesn't get warmed up at all. The two halves mix and result in a 20-degree increase in temperature from when they left the cooling unit, and that 20-degree increase goes back to the cooling units, gets dropped 20 degrees, and everything's happy. So you've hit on the goal. The goal is to have one delta T, have the delta T through the IT equipment match the delta T through the cooling units, and have the airflow rates match. And that is the most efficient way to end up. If controlling fan speed based on floor static pressure, does it make sense to run redundant crack units to lower overall crack fan speeds? Generally, the answer is yes. More cooling units running at lower fan speed, and this is regardless of static pressure control or not. Just any time that you put in variable speed drives and you're able to control the speed of the fans, regardless of whether it's being controlled manually or controlled by raised floor static pressure, it's more efficient to have more fans running at lower speed than fewer fans at higher speed. There's a bottom end to that. It depends on, obviously with chilled water units, the fan speed can go much lower than with air conditioning with crack units, DX units, but more running at lower fan speed is advantageous. And then we have the last one for the cooling capacity factor calculation. Do we use the nameplate ton capacity of the cooling units, 30 tons, or just the ton specified for sensible heat? Thanks, Louis. Great question, and the answer is you use the total nameplate capacity. You use the 30 tons because that's what you've bought, that's what you've paid for, and if airflow management and controls are configured appropriately, that's what you can get out of it. You can get more than the 25 tons of sensible capacity. You can get full 30 or maybe even more. So cooling capacity factor is intended to answer what is the utilization of that capacity that I've bought and installed. And so it is the full 30-ton rating. and not what is actually being delivered or what the cooling unit is capable of at those specific conditions. So unless anybody has anything else, I really appreciate all of your time and participation. And again, my contact information is there. Look forward to following up with you in detail if you would like. And hopefully you'll join us for the remaining 2 webinars of the month. Thank you very much. Take care, everyone.